and that is why we decided to celebrate it by calling four renowned mathematicians uh, to give a series of lectures on various aspects. I'll tell, the first lecture will be given by Professor Kalyan Vidhan Sinha, but before that I want to request our director to say a few things.
So thank you for inviting me to give this brief remarks on the occasion of Pi Day. I think it's a very important occasion. We all have learned from childhood, from the circle, how pi is defined, and there is a lot of history behind it. But I am not a mathematician, so there will be experts and we will talk about it. And my thing is that what I am very happy is that the mathematics department is doing something like this, and this kind of activity should be more, especially most of the mathematicians work more or less by themselves to a large extent, and it's not a group activity like experimental physics or chemistry or biology. And this kind of activities lead to more interaction and exchange of views and ideas, and I think mathematicians and maybe theoretical physics, one is sitting behind, right? They have to spend some time thinking and working individually, and then to exchange ideas or use others as the sounding board, what they're thinking, are they thinking right or wrong, and many interesting things come out of that. But what is even more happy occasion is we have such a famous person coming to ISR Berhampur, who was a former director of ISI and has been working continuously in mathematics. Everybody knows him, right? I came to know that he has a PhD in physics, is it? From University of Rochester, and then he moved into mathematics. So that is really very nice that he gravitated to a field which is normally people go away from mathematics. They go to applied mathematics, which goes into physics or biology and things like that, which are more glamorous, and remaining pure mathematicians is a kind of a small tribe of people who pursue this, but they all who pursue this have an inner passion to pursue this, and I think the drive is within themselves, and some very beautiful things come out, but it takes time. These things take time, and that's the story I once was discussing with probably you, the Fermat's last theorem. That guy locked himself up for 16 or 20 years in California. How many years? 6, 7 years, yeah. So, and then solved the problem. So there are a lot of things like that, and I'm sure all of you will be motivated by the presence of these distinguished mathematicians on our campus. It is different to hear people online and or read their papers, but when you meet physically, it is sometimes life-changing for many people. It has happened with me, it has happened with many people, that when you keep your whole life, that you get into something and you become passionate, sometimes you have one or two people you meet during your early life, that is when you are either graduating, master's or PhD, and that takes you in a different direction. So these physical meetings, which are very important, and especially more so in mathematics or theoretical physics, where it's not so heavy equipment dependent. It is the mind and how the mind works, which you come to know when you meet a person of that kind. So I have interacted sometimes in people, and some of those things I learned at that time, in which I was not doing research, came up useful later on in my life. And so in life, there's nothing called a waste of time. Anything knowledge, our brain is so sharp that you hear something I heard in 1984 talking to somebody. It comes up when I write a paper now in a different manner. And it is amazing. That's why you need the company of bright people. Environment makes a difference. That's why you need to work in a place where there are people who have great depth, who have worked for 40 years, 30 years, are very bright, and that changes the environment. So it is not equipment, it is not air conditioned room, it's not computers which matters. It matters the kind of people you interact in a place. Why Cambridge University is number one for 400 years? Right? They attract the best people almost for even small time also. So like that, you need to interact with the best people, best minds, and that's the objective I have started. After I came, we have initiated many programs so that we can invite people who are specialists and who have given remarkable contribution in the area of research to our campus so that you can personally interact and get motivated and be passionate. So yesterday I was discussing with them that C.N.R. Rao and Rodam Narasimha, two stalwarts, both of their FRS, one in fluid mechanics, that is aeronautical engineering, one in chemistry. Their motivation came because in school, class 5 or 6, they met C.V. Raman. So C.V. Raman came to their school, the National School, Jayanagar in Bangalore. And what I hear from C.N.R. Rao, that was his time that he started thinking very big. That is, those days in 1947, he could think of which is the best university in India. He could think of writing to a Nobel laureate. Who would have thought? Which kid of 15 years, 12 years will write to a Nobel laureate from India? India is not even free at that time. So imagine he is 30, 40 years ahead of his time. Okay? But that 30, 40 years ahead of time was one occasion which triggered this kind of chain reaction. So these are events which trigger a chain reaction in your life. And your life many times changes because of that. So with these words, I will stop here and I will say I congratulate the mathematics department to Prem, Vishwabrata, Rani, and one more name is there in that. Kashi? So for organizing and all other faculty of the maths department, the small department, I think we are 8 or 9. All our departments are right now subcritical, but I'm trying to see that they become critical so that chain reaction happens, like in a good area. Okay? So more ideas, more senses. So I thank all of you and wish you all the best and we should continue doing such things.
Okay, so thank you, our director sir, for giving very nice and enlightening, motivating lecture. So at this point, I will tell a few things about Professor Kalyan Sinha. So Professor Kalyan Sinha did his undergraduate in physics from Presidency College, which is now Presidency University. Then he moved to Delhi University for doing an MSc, and eventually he moved to Rochester for doing a PhD in physics and actually in quantum field theory. And after working for a couple of years and then a postdoc in particular at ETH, he came back to India, joined at ISI, that's Indian Statistical Institute, and slowly started working in the new emerging area called quantum probability, which was that time just initiated by Hudson, Robin Hudson and K.R. Parthasarathy, who was already there in ISI. As you understand that this ISER system is kind of like an place of interdisciplinary research thing, and he is also one of the few physicists who shifted from physics to mathematics and doing very pure mathematics and at the same time understanding the physical things also. So that is why we have, and we are so happy that he decided to come here. Just to add a few things about his achievements, that is, he is also a member of Indian National Science Academy and the Indian Academy of Sciences, fellow of, sorry, fellow of this thing. He also had a Bhatnagar Award, and he is also a fellow of TWAS, that is the Third World Academy of Sciences, and Bhatnagar Fellow. The world, okay. So the interesting thing is about this area of research is the following, that as you know that in the quantum mechanics which developed from the 1930, roughly around the beginning of the last century, and then it moved around 1930s, it created a synergy that a part of mathematics, that is a functional analysis, started moving forward, and it has become whatever it is right now. And then of course physics had its own direction, mathematics had its own direction. But at the same time we also see that many things also merge together. For instance, right now in certain areas of physics they are using techniques which have been developed by number theories, like p-adic geometry and analysis there. So Professor Sinha will give two lectures here. That is, first one is on a brief history of quantum mechanics. The second one will be more in the today's time thing, that is a quantum computation and how you can do it more mathematically. So I will stop here, but I will request our director sir to give a memento to Professor Sinha.
Is it on? Need something, but no. Do I sit still or what? You want me to? No, I will stand. Yeah. So how do I change the slides? No, I will change it. It's okay. Thanks. So let's start? Yeah. Well, thank you all, and a very good morning to you all. Well, I think whatever Ritubrata has said, one has to qualify it a little bit, and I think that's why I believe that a little bit of knowledge of history is always important, including the history of yourself, how you have evolved over the years. And for myself, it has been a journey, but there has been a considerable amount of different kinds of evolutions and branching away at several points in my professional life. As he said, after about a couple of years in masters in Delhi, and Delhi was supposed to have the best theoretical physics department of India at that time. Mind you, I am talking about ancient times, at least relative to you people. This is 1960s, okay? I am an ancient person, so obviously the relevant period is pretty old. But Delhi was supposed to have the best physics department, particularly theoretical physics department of that time. So I went there. In fact, I do recall the head of the Department of Physics in Presidency College, which was a premier college of that time. I'm afraid it has fallen into very bad times, as I am told. Presidency College is not what it used to be. He himself told me to leave Bengal and go elsewhere to study. And he suggested going to Delhi. So I went to Delhi. Is there any problem? Yeah, it's okay. No problem. Oh, it was affecting the sound. Is it too close?
It's better to be close because it cannot capture voice.
And you could see the difference. I do not claim to be anywhere near like Hardy, and something similar happened to England. In the person of Hardy. Before the war, Hardy took a trip after finishing his PhD or doctorate. Those days it was not called PhD. He took a trip to continent, that is outside England but Western Europe. He went to Germany, France, mainly these two countries. And he was appalled at the state of mathematics in England and the way mathematics was being done in France and Germany. And he thought that they were miles ahead of England in development of mathematics. So he came back and changed everything in England, changed the syllabus of Cambridge right away. First thing he did was to change the syllabus of mathematics in Cambridge to introduce more modern areas of mathematics to be taught. And that changed the scenario in England, mathematics scenario in England. And Hardy was responsible for that single-handedly. Of course, he was also responsible of many other things, some of which you may be aware of, including grooming of Ramanujan and many other things. So I went to Delhi, and beautiful new things were being told, which you cannot possibly hear at that time had I been in Calcutta. For example, groups, various transformation groups which are of great importance in physics, and their representations. Those were key ideas in quantum mechanics. In fact, you can do almost 90% of quantum mechanics just from representation theory of groups, modern quantum mechanics, if you have the right mind and the right apparatus. Of course, you have to have certain amount of apparatus, and that has to be developed. But then I went to Rochester, and I found half of the things I learned in Delhi were all wrong, plain wrong. Okay? So that's what I mean by evolution. I mean, you discover many things. I mean, they may be wrong, but at least the direction was right. Okay? The details were wrong, but the direction was right. And it is often very important to get the right direction. And that is, I would say often, half of the work is done if you have got the right direction. And I often tell my students, the proof of the theorem is not really the important thing. What theorem to prove if you can discover that? That is already half of the thing done. For example, I will ask younger persons present here, why do you think Cauchy went about doing what he did in his complex function theory? What would be his motivation at that time? Because Newton has preceded him already, Laplace has preceded him. Okay. As you will see about Newton, there will be things to be said about Newton. He was a great scientist, as all of us know, but he was a lousy human being. Okay? He was a terrible person as a human being. So let me begin with my talk. Now I have to do this, right? Okay, so I will quickly go through, because you see I actually gave this talk in JNC several years back, and my laziness prevented me from changing too much. But what I would like to do is to scroll through this part a little faster, so that I have a little more time left in the end. And I would like to impress upon you that how the basic thinking and understanding the direction is the most important thing, and rest are all details. Of course, you have to be technically well equipped to do the details. That's the second part of the game. But the first part of the game is to have the direction, what you want to do and where exactly you are going. Okay, so this is a historical journey. As I said, it is a brief history of quantum mechanics. Okay? So I would start around 1900. Sometimes I will go even behind, before that, but roughly 1900. So it is, quantum mechanics is roughly speaking about 100 years old, or a little more than 100 at best. So the black body radiation is the beginning. Oh, sorry, I used to. So these are the various events that took place in the 20th century, early 20th century, on the experimental side of physics. And they were discovering things which they understood, but there were situations which they did not completely understand. And there were, people were keen to understand it, but they were unable to understand it. And that's the kind of situation where you do the best. The uncertainty, the stress that you go through, that you are not understanding something right in front of you. So that naturally generates a stress. But that is the best medicine to produce good things. Without stress, you will not produce anything worthwhile. That keenness, that the drive, that I should understand this, but I am not understanding. So these were essentially the experimental background. So Einstein was a big player at that time. So Einstein, many people do not know that Einstein did not get his Nobel Prize for relativity. In 1905, I think he published 5 papers at the same time, of which this is one of them, photoelectric effect, for which he got Nobel Prize. Part of the reason is the Nobel Prize is often the theory and experiment are coupled, okay, in the prize. That's the reason often there is a difference, because there was no possibility of doing any experimental verification of theory of relativity at that time. Okay, so let me scroll. So that what was coming through is the so-called the dual nature of physical objects, whether it is light or whether it is so-called particle like electron. The word particle itself is a product of history. Okay? It has really no meaning. It has not been defined ever. So these primary concepts of science are never defined. Okay? And that, of course, is the beginning of a problem. It is like the so-called point in geometry. You cannot really, you have to start with an element, and the only way to define it is by abstracting it. Okay? So the geometric optics was already in place. So I think Professor Ganguly was mentioning Fermat's last theorem, but Fermat was also known for other things, namely Fermat's principle that light has a trajectory, and it takes the trajectory between 2 points, which takes the least time. Okay? So this is something which preceded by maybe as much as 100 years. There are other extremal principles which are found very useful in many parts of natural sciences. For example, Hamilton's principle of least action. These are all extremum principles for optimization problems. And so mathematically, it is an optimization problem which leads to differential or partial differential equation. They are intimately related. So that's the mathematical side of it. From physical ideas, you get this optimization principle. Like Fermat believed that the light will go from point A to B, it will take only that path which takes the least time. That's a question of belief, or maybe experimentally you can verify it sometime. But then it becomes a mathematical problem. You find it, what path it will take. Once you have enunciated the problem, then it becomes a mathematical problem. Of course, he couldn't solve it at that time. He had to wait for maybe 100 years or more, because calculus has not come yet. Okay? He had to wait for Newton and Euler. Mainly the first person who solved was Euler actually. Lagrange was a young man of 18 or 19, when Euler was already about, I think, 40, 50, something like that. Euler was a blind mathematician. He was not born blind, but he became blind. He was a Swiss, German Swiss. But Switzerland was so poor at that time, he could not find a job. So he took a job in Moscow, in the observatory of Moscow, astronomical observatory. Here is a mathematician in search of job, goes to an astronomical observatory. And there he continuously worked. As you know, probably that Euler was one of the most prolific solver of problems. He left behind nearly 700 odd papers. Yeah? That's an astronomical number of papers for a mathematician. So Euler who solved the optimization problem. Okay? But he learned that Lagrange in France has already also solved it. And Lagrange was 19-year-old. So he withheld his publication so that Lagrange can publish earlier than him. Okay? So then he published, and it came to be known as Euler-Lagrange's solution of optimization problem. So that's how the theory of optimization started, evolved, etc. Okay? But it was motivated by a physical problem. So I wanted to give you examples, and there are plenty. Wave optics. I'm sure you have gone through this at some point in your school. Geometric optics and wave optics. Now Huygens proposed it. This is a Dutch physicist, but Newton didn't like it. He was a contemporary of Newton. So Newton suppressed it. He didn't allow it to be published for many years. That's why I said Newton was a very nasty person. Because he believed in the particle nature of light. He called it the corpuscular theory. So he suppressed Huygens. Then came well after Newton came the interference experiment of Young. And then there was no way, Newton was gone anyway, so Huygens ideas came back. That is, wave optics made a comeback. But curiously, Newton actually did interference experiment, the famous Newton's ring. Actually, I've gone to Newton's house and I saw this, and I remember the visitor, the guy who was taking care of his house. He said, "This is the bed in which Newton slept." I said, "Don't kid me. That was 300 years back. That bed is still existing." This is Newton's house. So it is a museum now. People go there to see. So Newton's rings are there. So he made those experiments in 1717, the famous experiment of Newton. So Maxwell, electromagnetic theory, Maxwell was not an Englishman, because if you tell that he was an Englishman, if in front of him, he will kill you. He was a Scotsman, okay? And Scots people don't like to be called Englishmen. And Maxwell's equation predicted wave solution of propagation of something which has a certain velocity. And this velocity of light was measured by people experimentally. Michelson was the most accurate one of that time. So the velocity of light played a very important role in development of many theories of physics. For example, relativity theory, velocity of light plays a central role. In fact, it is quite curious that velocity of light, why should it play so curious role? What is so profound about light that other physical entities do not experience? Why light velocity is so universal? It is not clearly understood. Experiment, but at the same time, or actually before, another subject was emerging in physical firmament, namely that of thermodynamics. So these are developments which actually meshed together in the 20th century extremely well, and various areas of mathematics evolved with their evolution. Okay. So Maxwell and Boltzmann, they also looked at the what are called kinetic theory of gases, that is, what constitutes a gas. So there are objects there, let me not give them any name, which are running around madly, some velocity, banging against each other. Question is, how do I treat such a physical system? So their concept of probability was emerging, though actually concept of probability is already there. As you can imagine, the natural source of probability theory would be gambling. And from gambling evolved the theory of probability. In fact, Pascal was asked by one of his gambling friends to help him make winning bets. So that's how Pascal solved some of the early probability problems. No, but he had gambling friends who gambled, and they knew this guy is a very bright mathematician, so he wanted to go and they wanted to go and get his help to see that if they can get a good tip, which will make them win. Okay? I don't know whether they won actually. I mean, the story doesn't say whether they won, but he helped them. Yes, Pascal was very religious. So the question came that around the end of the previous century or the beginning of the century, that the energy that a so-called black body, that's something which you should the paint black in some way so that it does not reflect any radiation that falls on it. It absorbs everything. So what they wanted to know, what is the distribution of energy inside such a body? And Rayleigh and Jeans, they are English physicists, they worked out and they showed that it is proportional to the square of the frequency. But then, so that was very nice and they could see that it is more or less tallying with the experiment. So much so that Lord Kelvin alleged to have stated that there is nothing new to be discovered in physics except to improve the decimal place. But he was in for a shock. He was proved wrong within a decade by the jolts of quantum theory and relativity. So Rayleigh-Jeans law was correct in the low frequency domain, but quite incorrect in the high frequency domain. So classical theory was getting to be inadequate in the high frequency, which means effectively high energy domain. So 1900, Max Planck, German, appeared. Now what did he do? He just out of the air, he made a hypothesis that energy is not exchanged continuously like in the classical theory. Because in classical theory, you see why things are like that, because it is all due to Newton. Everything is essentially predicted by solving differential equations or things related to some kind of a differential continuous change. And therefore, the energy also is essentially either absorbed or released continuously. Okay? But Planck made this bold hypothesis, that's not happening here. That the exchange of energy is not continuously, but in multiple of an integer. A constant multiple of integer. So it is what is called quanta or quantum hypothesis. So the word quanta was used, not quite first time, but early use of the word quanta. That electromagnetic wave energy also is absorbed or released in multiples of integers. And that constant integral multiple of frequency, and the constant of proportion is called Planck's constant because of obvious historical reasons. And Einstein's theory also came soon after, and Einstein used Planck's hypothesis of the release and absorption of energy in integral multiples of frequency. Now, integral multiple of frequency, I think that's mine. If the physicists of that time or soon after, if they talk to some of the mathematicians, particularly the really good ones, they would have probably got a hint already. The mathematicians were already looking at such things. In fact, 2 decades before 1900, they started looking at similar problems. In linear algebra, I think you are taught today in probably school or college, or the eigenvalue problem. So, because Hilbert is already around, and you will see more about Hilbert soon. So, this quantum ansatz of Planck was a revolutionary ansatz. And you have to think with the mindset of that time. Otherwise, you will not appreciate really what kind of a stress the scientists faced when Planck came with his hypothesis. Most people just threw it out, saying that is all nonsense. Now, little more mathematics started appearing on the horizon. So in classical mechanics, which is has more to do with continuum, differential structures. I am not using the word equation, differential structures. And parallelly, mathematics has evolved already. The differential structures are already in place. And Poincaré is already around. So he actually reformulated a lot of classical mechanics. Hamilton and Jacobi did it of before. So these are mathematicians. Hamilton and Jacobi, both are mathematicians. Both are, Jacobi is very famous mathematician, German. Hamilton is Irish. Ireland was a very poor country. So Hamilton died around the age of about 40, 42. He came from a very poor family. He had essentially died of starvation. So he formulated whole of classical mechanics in terms of these integrals over a kind of a manifold. Okay, so the idea of differential structure, as I said, has already emerged, and the classical equations could be derived from variation of a certain integral over a manifold. That is Hamilton-Jacobi theory of classical mechanics, actually. Now, what Sommerfeld and Wilson hypothesized that those integrals will be multiple of some constant, again Planck's constant. In other words, they were trying to redo Planck's ansatz in a little more mathematical structure. So this theory started being called the old, now called the old quantum theory, and it has been discarded completely. Oh, did I do something wrong? And Bohr, who was a Danish physicist, he introduced that, I think this is equation, that classical theory can be recovered as a limit of Planck's constant going to zero. Now, of course, it doesn't make sense, but mathematically it makes sense, but physically it is absolutely meaningless, because this constant h has a certain value. In fact, I wrote a few pages back, I wrote the value there. 6.6 into 10 to the minus 36 joules second. That joule is unit of energy and second is unit of time. So how can that go to zero? It is a very small number, all right, but that's another thing, and saying that it goes to zero is quite another. But nevertheless, he tried to understand this transition from this new quantum theory to classical theory, which they were more comfortable with. Because remember, they are comfortable with classical theory because they have grown up with it. And suddenly this upstart comes and makes all kinds of changes and says this is a new theory. So to give you an idea of the energy scale that we are getting into, so a 60 watt, normal 60 watt bulb of old time, not LED, LCD, is approximately 10 to the power 24 times average energy associated with a spectral line of hydrogen atoms. And to give you a perspective of these numbers, how large they are, the age of the universe is only 10 to the power 14 hours. So that 10 to the power 24 is a rather large number. So now comes situations which are, even today I would say, not completely resolved. So Dirac, one of the creators of quantum mechanics, in 1930 in his book, he says, in order to give an absolute meaning to size of the system relative to the observer, so I am the observer and this is the system I am observing. Okay? This is very large, or not very large, it's almost comparable to the size. Okay? But if I look at a building, that of course is a much larger size than me. Okay? But if I look at the chalk, it is much smaller. So if you go to the atomic scale, that is much, much, much smaller. Okay? So that's what he is trying to say. But note the last sentence, such as is required for any ultimate theory of structure of matter, we have to assume there is a limit to our powers of observation and smallness of the accompanying disturbance, a limit which is inherent in the nature of things. That means as if he is invoking a supernatural object, we cannot transgress it, which is inherent in the nature of things and can never be surpassed by improvement of technique or increased speed. It is almost in some omnipresent supernatural entity. And there is this problem of the observer versus observed. So much so it came to be, the controversy came to be so much so, who observes the observer? The observer is making an experiment and trying to measure something. Okay? So I throw in a signal, I get something back, I interpret it. Now, that I am doing it. Someone else should observe the observer who is observing the system. So that it leads to an infinite regression, which is logically is quite a disturbing thing, because who ultimately breaks the regression. So you can go on doing this forever, infinite regression. This is called the paradox of infinite regression in quantum theory. So these are the pictures of some of the players of that kind. So Heisenberg now coming in as a young man. So he just finished his thesis in Munich under Sommerfeld and then went as assistant to Max Born in Göttingen. Now, except for Heisenberg, I think most of the players were Jewish. And 1925, we were coming to almost the time of the rise of Hitler in Germany. So Jews were becoming, their situation was becoming untenable. So many of them tried to leave before the war started. Max Born was one such person. And in fact, he looked for a job in India. You won't believe it, but he looked for a job in India. He came to India because of C.V. Raman. He came and visited C.V. Raman in Bangalore, stayed for several months, even taught. Then he went back. Something did not click, he went back. But he did look for a job in India. And then he left, he went to England, actually. He left Germany, went to England. So Max Born found that Heisenberg is getting an interminable array of numbers, which he could arrange in a certain particular way. And Max Born did attend some of the lectures of Hilbert in Göttingen and told Heisenberg that this may have something to do with matrices, what mathematicians call matrices. Matrices were found by mathematicians several decades earlier. Okay? In fact, determinant was found before matrices. Because determinants appear naturally in calculating volumes of various bodies. That's why determinants came out. So this led to what was called matrix mechanics at a certain period of time, okay, by the physicists. So then came Schrödinger, okay, Austrian, again Jew. He also ran away. He looked for a job in India, but he didn't get a job in India. And he ultimately settled in Ireland. So they were all running away from Austria, Germany, etc. Jewish people were all running away. So he looked at it this way, that these quanta are nothing but eigenvalues of certain partial differential operators. So you see, the scope of mathematics is changing, evolving. The partial differential operators are showing up. So on the one hand, you have matrices coming from Heisenberg, Born, etc., influenced by Hilbert. On the other hand, Schrödinger said these same numbers can be obtained as eigenvalues of partial differential operators. how were they related? In fact, I think Dirac made a leap of imagination. He said, two are the same thing. They are unitarily connected. In a Hilbert space, they are a single object but in different representations. That means they are unitarily equivalent. Different representation means unitary. So you see how mathematics is entering. So you have to have a Hilbert space. You have to understand what a Hilbert space is. And you have to understand what a unitary map is. So Hilbert space is making its entry into quantum physics. And Heisenberg proved his uncertainty principle, so-called that the uncertainty imprecision measurement of position and momentum has a lower limit. This is mathematically actually nothing more than Cauchy-Schwarz inequality. Little sophisticated use of Cauchy-Schwarz inequality. And the point is, the lack of knowledge makes you think that you are doing something, but actually it is the same thing that you are repeating again. Similarly, there are famous inequalities or famous results in statistics, mostly due to Sear-Rao. Okay? Like Cramer-Rao inequality, Rao-Blackwell, etc. They are also not much more than Cauchy-Schwarz inequality, but in an appropriate context. So one of the thing I want to tell you is that if you have the mind open and if you are a little bit careful in observing things and discerning patterns, you can prove many results in different areas using the same mathematics. And my next talk will tell you again another area, namely so-called quantum computing or whatever, how again simple mathematical ideas you can use in different areas and get some interesting results. So these are the players at a slightly later stage, maybe a decade later than the previous players. Heisenberg, Schrödinger and Dirac, they are pictures. Heisenberg was a very bad student. He almost flunked. In fact, Sommerfeld protected him because his external examiner was an experimentalist and he was meant on harassing him. Okay? And so Sommerfeld actually had to intervene to protect him, otherwise he would have failed his PhD. And Paul Dirac, Englishman, he was an electrical undergraduate electrical. Then he got taken by quantum theory and moved. So Dirac brought more mathematics into physics. He had at least good knowledge of linear algebra, which is a lot to us of a physicist of that time. They knew differential equations. So Newton had taught them that differential equations are necessary to understand various physical. But they did not know linear algebra. So Dirac came from electrical engineering. He introduced more concepts of linear algebra and tried to understand quantum theory that way. So Hilbert and Riesz pioneered mathematical analysis that phase during early 20th century. Paul Dirac introduced investigative mathematics, and he actually solved this dichotomy between Heisenberg's matrix mechanics and Schrödinger's wave. Two combinations of two different representations of the same theory in a function space. But of course, he was not very precise about what kind of precise function space he was looking at. That had to wait. Because the mathematics had not developed enough yet. They are waiting for Lebesgue to come. Lebesgue had just come. He was giving his teaching Riemann integration. He told me. You are also teaching Riemann integration. Okay. So Riemann integration. Oh, you are teaching Lebesgue. Okay. So Riemann integration already existed. And No, Riemann integration existed in the sense that vague ideas were there, like that is because even Archimedes had used what is called Riemann to you 2000 years back, not 200, 2000 years back. So he calculated volumes of various regular polygons and regular surfaces, area, etc. All those things. But actually, I won't use the word larger, but a different class of function. Because we demand to get roughly speaking, essentially continuous. But we want to get away from continuous function. And that had to wait. That function of quantum had to wait till the great master had appeared on the scene. So this is again back to physics. So quantum theory now comes the next level of quantum theory. Namely, here, so far people have studied quantum theory of particles, whatever that particle may be. The word particle has never been defined. Okay. Mathematically, it is absolutely fine. So, but now we want to do quantum theory of fields. That's the next level of challenge. And so that led to this Dirac's problem. The Laplace operator had already appeared in Laplace by himself. Of course, he was introduced the Laplace operator when he was studying electrostatics problem. That's where Laplace operator comes first to solve problems of electrostatics. Some of you may have studied it already in physics. But then he found that that does not solve certain contradictions in the physical theory. Pauli and Heisenberg. So to get around that, he needed a leap of imagination, and Dirac provided that. You have to extract the square root of the Laplace. Namely, Laplacian is a second order differential operator. You want to convert it into a first order differential. Extract a square root. Now, extracting a square root is easier said than done. If you found out, you can't do it. Not in the field of complex numbers. There is no square root. So roughly speaking, if you want the abstract mathematical description, it says we have a quadratic form, which is not necessarily positive definite. You want to extract the square root of the quadratic form. It has to be linear in the vectors. Okay? So how will you do it? Like Dirac found, you cannot extract a square root in the field of complexity. You have to go beyond the field of complexity. So he solved it by using matrices. So he found that there are certain 4x4 matrices, which, so those are the coefficients, matrix coefficient factorization. Now that theory became, so this is a mathematical question. What Dirac did is to solve this problem coming from physics. Because second order differential operator led to some inconsistency. You wanted to take the square root. That led to the question of extracting square root of quadratic forms. Can you do it in complex fields? You cannot. Not in general. Okay? So that led to what is Clifford. He studied this question by itself. He studied as an abstract question. He solved it completely. Those are called Clifford algebras today. Okay? What Dirac did is to extract the square root, okay, of a particular quadratic form. Okay? And he found that you cannot do it in the field of complex numbers. he took matrices and he could solve it in the field of matrices, 4 by 4 matrices. So those who turned out to be representations of a certain Clifford universe. So you see how the physical question led to, about the same time, very deep mathematics. And Clifford algebra later on found a considerable amount of use in describing things like Atiyah Singer's index theory and so on. Deep part of topology. Okay? So I want to give that message that here is a challenge you face. You take a leap of imagination. You don't really know that everything is just hunky-dory. It's not necessary in the first place. But what is necessary is to take the leap of imagination. Don't get bogged down by technical details at the first attempt. First attempt, let your imagination go. Of course, you have to then sit down and try to do as much as you can to justify it. It was not a simple thing. It took people several decades to solve the problem. So it is something futile to expect that you will do it in a few days. It doesn't happen like that. But the idea is the first thing. Without an idea, you will be just solving the back of the book problems. So, epilogue, from finite to infinity, von Neumann enters the game. Lebesgue has already come. So, Lebesgue integral is in place. So, von Neumann expanded the subject matter very quickly. He particularly wrote his book, Foundations of Quantum Mechanics, 1936, unreadable. You try reading it, it's unreadable. Because his notations were so clumsy of that time. Now, Schrödinger problem was reduced to the eigenvalue problem of a self-adjoint operator in the Hilbert space L2 of R3. Now, this L2 of R3 is so-called Lebesgue space. That's why I said it had to wait for Lebesgue integrals. Otherwise, you have problems. You cannot have just a function. You have to have an equivalence class. And that is a major issue which von Neumann handled. And von Neumann went on, of course, as you may know, von Neumann was a polymath. He could solve just about any problem that came to him. I don't know whether you know that he wrote a paper with Chandrasekhar, S. Chandrasekhar, on scalar dynamics. And he also designed the first computer, and even today, all the computer architecture is called von Neumann architecture. And then von Neumann addressed this problem that can I work in a quantum system without referring to the Hilbert space? So he produced with someone called Murray in Annals of Mathematics, with 5 papers, the rings of operators, created a new area of mathematics. Now they are called operator algebras. And then what Dirac had said decades earlier, is there anything I should know? That see, when you want to prepare a state, okay, you want to know what is its position, or how is it falling, or is it steady? Of course, it will break if it falls, but it doesn't matter. Or even it doesn't have to fall, if you just write, then it will break. These are infinitely difficult problems. To write, they just keep on getting smaller and smaller and smaller. So what Dirac called is, how do you know something is what it is? You have to do experiment on it. But in quantum theory, unlike classical theory, if you do an experiment, you disturb the system. So how many experiments you can do without disturbing? That is called the maximal set of compatible observations. And mathematically, von Neumann interprets it as maximum abelian subalgebras of certain operator algebras. It is an area of major study even today in mathematics. And Neumann, as I said, with Garrett Birkhoff, the senior Birkhoff, not the guy who wrote the book on differential equation. It is, I don't know whether they are related, these two Birkhoff, but this is a famous Birkhoff, G. Birkhoff, in Harvard. And von Neumann, they wrote two papers. They did not write too many things together. First was what is called quantum logic. Okay. So von Neumann essentially observed that unlike the classical logic, which is a Boolean logic, the Boolean logic essentially has one distinguishing feature. The De Morgan's law is valid. That means union distributes against intersection. This is violated in this logic. So he introduced a logic as a non-distributive lattice. Lattice is an algebraic structure which was already known to mathematicians. So with a non-distributive lattice, that means what De Morgan's law is no more valid. So what kind of mathematics can you do with such a lattice? That's the question. And they could do a lot. So for example, it is not completely solved problem, but so given such a non-distributive lattice, you assume a few more properties and try to show what is the representation of such a lattice, what are the representations, and what many people could show that they are represented as orthogonal projections in a Hilbert space. But what they could not pin down is the field over which the Hilbert space. Physicists had determined by that time that it is only the complex field that matters in physics. That is the Hilbert space over complex field. So, but this von Neumann's direction of using quantum logic, what was called quantum logic, it is called quantum logic because Boolean algebra relates to the classical logic. In that sense, it is called quantum logic. It has nothing to do with logic actually. So the representation of those non-distributive lattice turned out to be projections, orthogonal projections in a Hilbert space. But it could not be, you could not pin down the field. That even today it is not a completely solved problem. That means if you add one more axiom or some property, will it pin down the field? People did do a little bit by adding one or two more hypotheses or axioms. They pin down into characteristic zero. That's it. After that, no further progress. Okay. Okay, so here I've already said this. Now this linear structure of the theory, it is a vector space. That is what I mean by linear structure. And that is, you can take two states and make linear superposition and you get another possible state. Unlike in classical mechanics, you have one trajectory and you have another trajectory. You cannot, by linear superposing them, you do not get another trajectory. Not true. So Newtonian mechanics is basically non-linear. Quantum mechanics is linear. So you could say, you would immediately jump in joy. Well, linear theory is much easier than non-linear theory in some sense. But joy will be short-lived or infinite. That means its own mathematical fact that you have to ideas has been done quite a bit. Now Now, Feynman in 1982, long time back, observed, this is just an observation of Feynman, but then Feynman would make off-the-cuff remarks which will set a trend often, that he thought the superposition principle of quantum mechanics should allow a different kind of computational architecture in which the set of available states increase dramatically. Architecture has not changed, but states have changed. And that is what has holds some hope that there will be a quantum computer someday. So I have said this, that Newtonian mechanics is a nonlinear theory. In fact, that being so, that's why in the early days in Europe led to the creation of differentiable manifold, because actually to understand the Newtonian mechanics mathematically, you have to create and understand this concept of differentiable manifold, differential symmetry. That is automatically is deeply connected to the classical mechanics or Newtonian mechanics. So you see how mathematics is joined with a certain area of physics, okay, and corresponding mathematics. Of course, mathematicians will go their merry way, okay, but the initial impetus came from that, to create this structure of manifolds, because linearity you have lost. Okay? So you have to generalize your theory a little bit more. It is no more a linear space to understand Newtonian or classical mechanics. Whereas quantum mechanics, you have to understand infinite dimensional vector space and maps or operators. That is what part of what is called functional analysis, that is mathematical discipline. Okay, give me 5 minutes. So this is essentially the bare bone of modern quantum theory. So state of a quantum system is given by a vector in a Hilbert space. That's not completely true. That's why I have written more generally a positive stress plus operator of trace 1. So it is like, if you take these are called density matrices, again for historical reasons. I don't know, von Neumann apparently introduced the terminology. I have no idea why von Neumann introduced such a name, which is very poor choice of name like this. But the stuck, everyone uses the word density matrix. This is nothing but a positive stress class operator of trace 1. Now, you see how another mathematics is just about trying. It is like a little egg from which the hatchling is trying to come out. Okay? Have you seen it? In pictures, it takes a little bit, and it takes maybe an hour or two before it actually comes out. But here we are talking of concepts. It takes a decade or two before it actually finds the shape. So observable, this is terminology, something which you can observe. That's why it is called observable. Self-adjoint operator is the mathematician's terminology. And this is a highly non-trivial statement. I give you a map. How you know it is self-adjoint? And this was developed by von Neumann. The whole theory of self-adjoint operators is due to von Neumann. And how I give you a self-adjoint operator? You are in an infinite dimensional space. You have a self-adjoint operator. People who know a little bit of functional analysis, I can say that the self-adjoint operator most often will be unbounded. That means it will not be defined on every vector in the Hilbert space. Only a certain set of vectors on which the map will be defined. The domain is strictly smaller than the whole space. So that being so, you cannot form a square, you cannot form a cube, not necessary. Because the range may not fall in the domain, so I cannot apply it again, so I cannot form polynomials. The mathematics has to change. Polynomials are out of your range. So what kind of function? So why polynomials are important? Let us come on some simplest form of function. But as soon as we go to the, let's say, infinite line, polynomials are not going to give you everything. Only on interval polynomials are good. What do I mean by this? That will be the theorem. You have studied it, you have come up here. Weierstrass's density theorem. Polynomials are dense in continuous functions over a space. Or you can uniformly approximate every continuous function by a suitable family of polynomials. That's why polynomials play a major role in analysis or in applications whenever you have compact domains. But as soon as you clear, can you be a little louder, please? No, now you see, no, you are going to infinite series. Okay? That's a different entity. Infinite series are not polynomials. In infinite series, immediately the question of convergence arises before you even proceed next step. But exponential functions, of course, that's a very nice function. So it is infinite series, but we know that it is a nice function. That means by nice I mean it is infinitely differentiable. But at infinity it blows up. You may say take e to the power minus x, then it blows up in minus infinity if you are taking the whole real line. Okay? So that is not going to help you. Okay? So what kind of function would you really look if you have the whole real line? That is the question. So one possibility is if you go to trigonometric functions. Where does the trigonometric function appear? Today is a pi day for you guys. So you should be able to connect pi with the trigonometric function. That's the natural habitat of trigonometric function. Tell me, pi comes from where? What is the origin of pi? Probably Archimedes, or even it was known before Archimedes. But Archimedes was the first to really pin it down. That's more than 2000 years back. So it is a long time back that pi was well known. Where did it come from? That's my question. It came from circle. Circle, geometry, numbers, analysis, they are all connected. They are not really different. So such a function on a circle, whose domain is the circle, naturally trigonometric function will appear when you approximate a function on a circle. That is the job of, that is how trigonometric function appears. Fourier series, trigonometric function, continuous function of circle, they are the same thing. This is a Stone's theorem on the circle, which tells you that any continuous function of the circle can be approximated by trigonometric polynomials. That is Fourier expansion. So it is Stone's theorem not on an interval but on a circle. But then an interval can always be mapped into a circle by identifying the two endpoints. What does it mean for the interval? Periodic. To identify two endpoints of an interval, identify means you are actually making a circle. Right? And that's why periodicity is the way to express that you have mapped the interval to the circle. So periodicity is a nature which will come from Fourier series, right? Trigonometric functions are all periodic. That's why they appear. This is a topological geometric statement being expressed in terms of functions. That is the way you should look at the previous. That's the way you should look at the previous. Now, if you take a circle, but think of it. So circle, if I have a, think of a little string or infinite string of very large, I'll make a circle, okay, of radius 1, let's say, and let it wind on itself. If it falls on itself, on top or from bottom, okay, you won't recognize that there is only one circle or two circles or 10 circles or what are you mapping? You are mapping the whole real line into something. Going below is the minus infinity, going above is plus infinity. Okay? So in other words, if you stretch this string, you will get the whole real line, minus infinity, plus infinity. But you have mapped the whole real line into infinite number of circles falling on each other. So your mathematics will automatically reflect this. That's why mathematics aim this topology. This is a part of topology. How many times it go round? N is an integer, positive or negative. And that integer is a topological integer. So, geometry, topology, analysis, kind of mathematics that will come will be dictated by the problem you have. If your mind is open enough, you ask the right question. So, I would like to really impress on you, particularly young people, start to think and ask the questions to yourself. You don't have to ask the people. Just because you can't answer them doesn't mean you get, okay, exam is different. But I am saying, just because you can't answer the question, you should not get frustrated. I go to the teacher and ask. No. Ask yourself. Continue to agitate in your mind about the problem. You will get a picture. And then it may just show itself to you if you ask the right question. So similarly, you see, for example, here, this is the beginning of another mathematics, namely a new kind of probability. And that is the way von Neumann wants to look at. He wanted to look at quantum mechanics as a new kind of logic that I have said for the sake to describe. He wanted to look at quantum mechanics as an analysis in infinite dimensional linear space. And then also, you can look at quantum mechanics as a new kind of probability theory. And the last part is essentially trying to give a glimpse of that, and that is von Neumann, who died at the age of 55. And there are many stories about von Neumann. Some hard or he was an extreme conservative, right-leaning person, politically very, very right-leaning person. He was involved in the manufacture of the second bomb, that is the hydrogen bomb. Not the one about the movie that you saw, Oppenheimer. That is that. That is the first bomb, the atom bomb. And von Neumann was involved in making of the hydrogen bomb, which came later, which you must know explosive power, etc., etc. But the story is one of the book of Feynman. Some of you must have read it. You must be joking, Mr. Feynman, that book, in which he writes about, he was also involved with the same project, Feynman. So he writes one place, they were asked to estimate the amount of explosive power that the bomb will have from first principles. before they make the bomb, they would want to have an idea of how destructive it is going to be. So 4 or 5 people were interested with that task. Feynman was one, von Neumann was one, Fermi was one, another very distinguished physicist, Fermi, was one, and so on. Fermi was using, he was very fond of and very good with using slide rule. I don't know, have you guys seen a slide rule? You are too young to have seen a slide rule, I think. But you have seen? You see that before the handheld calculator came, there was a slide rule in which, you have a little ruler-like object with the middle part where something can slide in and out. Using that, you could multiply and divide and so on and so forth. Calculate up to a certain order of correctness, decimal places, just using this. So this was devised around, I think, 1940s or so. So Fermi would use that to calculate the yield. This is written by Feynman. Feynman would use this desk calculator. Some of you might have seen it. The statistics people use to calculate mean, mode, median, and God knows what else. And it is also used by people who want to use a lot of data to calculate various things. So these things have gone out of fashion, obviously, because computers made all these unnecessary. And Feynman writes, von Neumann is dead. Von Neumann never used computers. He was phenomenal in his head. He could calculate a large amount of calculation just in his head, number calculation. So that is, I think, the mind. Okay, there is this thing now which is collapse postulate. This is another thing which you will see in my second talk also. You see, this is very, very unique to quantum mechanics. If you have if you are in a state given by a vector f in the Hilbert space, and you make this measurement given by this self-adjoint operator A, and you find the value lambda 2, then any further measurement on the system will only give you lambda 2 back again. Okay? Nothing else. So this is a big problem. The system collapses to the eigenstate. What and how? Whatever form. It was in a certain state as soon as, so you are making observation A, like position and so on. Then A, say, is a self-adjoint operator with various eigenvalues, lambda 1, lambda 2, lambda 3, etc. You find the experiment that you are finding lambda 2, let's say. Okay? But then the future of the object is sealed. It will remain in that eigenstate forever. And this is the part of thing which is even today not properly understood. The reason is there is no measurement theory of measurement. What do I mean when I say I'm observing? Or observing is just a measure. What is observation? Whatever you see. You see me, I see you. What does it mean? Light from here is reflecting from you and it is receiving, my brain is interpreting as you are sitting there. Okay? All these phenomena is going on. Now that's why you see this light won't be able to see an atom. The atom is too small, it will not reflect anything. Okay? Or my eye is so poor as an instrument, it cannot see the reflection coming from such small object. In fact, what famous optics physicist Helmholtz, some of you may have heard his name, once said, he studied the human eye quite one of the earliest. He said, if human eye was available in the market to buy, I won't buy it. But he was, of course, exaggerating because it has other abilities which machines don't have. But as just observation of like human ear, is extremely inefficient instrument. The dog has a better ear than human being. Okay? So, what you observe depends on not just what you are observing, but also the observer. For example, as you know that some dog barking you cannot hear because they are barking at a frequency which is beyond human ear's capability to hear. Does it mean that dog doesn't exist? How do you know it exists? If you have not observed it, how dare you say something exists? Or should you say something exists? So this can bring you to essentially some kind of philosophical domain, okay? I think ancient Hindus also did deliberate about it, okay? Like it is alleged that Shankaracharya said that everything is illusion. Okay? What you see is not your seeing, it is just your thinking you are seeing. Then there was this, he called it Maya, everything was Maya. Then someone said that, well, I mean, or a rogue elephant came and Shankaracharya allegedly ran up a tree to save himself. Then his disciples said, sir, why did you run up a tree? This elephant is a Maya. It is not really there. Why did you run up a tree? They said, who said I ran up a tree? That is also Maya. So, point is, you enter such philosophical domain which obviously cannot be resolved at all. Okay? So we won't enter there, but that doesn't mean such questions do not exist. Such questions exist, and not everything can be answered. So of course you have heard the Bell's inequality, something you have heard, right? This was, there was a question raging for many years that, I mean, the difficulty is words cannot express always everything that you really want to say, because words are hampered by the structure of the language that you are using, and language was not created with the purpose of expressing science or mathematics. Therefore, language, any language, is to some extent inadequate for doing mathematics or science. But nevertheless, we will have to do it to communicate, otherwise we might as well stop all lectures and sit at home. Okay? So, what I wanted to say that the question that agitated people was that is there a world, okay, that means what we are seeing as a quantum world. And quantum world is real, it is very successful, it has produced enormous things for the human being. Okay, almost everything you do today is due to quantum mechanics. Okay? Starting from your, forget computer, starting from your, whatever you use, I can't think of immediately. I mean, of course, this thing that is projecting, everything is possible due to quantum mechanics. Okay? But there are questions which you cannot answer. So you are in a very disturbing situation. So of course, it's not clear why we should be able to answer everything. No, that's okay. This is done. Yeah. So it is like in mathematics also. Some of you may be aware that if you ask too many questions, you can't answer anything. The famous Gödel's paradox. That he showed that give me any axiom system, I can find a statement which can neither be proved nor disproved. That means the axiom system is incomplete. Now, if that is so, if that is indeed true, then we should all give up and go home, because we have no hope of resolving anything completely satisfactorily. But that is not true. Many things we do, despite of these inconsistencies, are amazingly has found application beyond any degree of imagination. Axiom of choice is one. Some of you may have heard this axiom of choice. You can neither prove it nor disprove it. But without that, an enormous amount of mathematics will just go down the drain without axiom of choice. Thank you.